Okay, so this week's lesson, practice, and assignment is on arithmetic and geometric series. So last week we talked about arithmetic and geometric sequences. So the good news is a lot of what we talked about with sequences applies for series. There's a different formula, but it's the same type of pattern, and the symbols that are used in the formulas still mean the same thing that they did when we were talking about sequences. So for series, still the same type of pattern. If it's a series, though, we're going to be using our S sub n formula. S stands for sum. So if I want to take an arithmetic sequence and turn it into an arithmetic series, all I need to do is replace these commas in the sequence with plus signs. And now instead of a sequence, it's a series. And I would be looking for the actual sum of all the terms. So for this particular example that I gave you last time, if I wanted to find the sum of that arithmetic series, we call it a series as soon as we put the plus signs in, I would just add all the terms: 2 plus 9 plus 16 plus 23 plus 30 plus 37 plus 44, and the sum is 161. Okay, so same type of pattern. You are adding or subtracting the same value. It's a linear constant increase or decrease. But instead of wanting to know the value of a specific term, we want to add up all the terms together. So in the formula, we still have n. It's still the number of terms. It has to be an integer. N has to be an integer, okay? Because you're talking about the first term, the second term, the third term, the fourth term, the fifth term, etc. There is no 5.5 term. A sub 1 is still the first term. A sub n would be the value of whatever term this was talking about. So if this was talking about, if n was 7, I would want to put the value of the 7th term here. So if I were using this example, this has 7 terms. If I want the sum of the first 7 terms, n would be 7 and a sub n would be 44, because this is the 7th term. Remember that n and a sub n would only end up being the same value if the 7th term was 7 or the 10th term was 10, which does happen sometimes. And then when we get to geometric series, again, it's the same type of pattern, except we want to add up, we want to add up all the terms. Series is just the sum. So here we are going to take this formula. Notice it says r cannot equal 1, because that would mean that we would just be multiplying by 1 each time, which means that every term in the sequence would be exactly the same. Like 2 times 1 is 2, 2 times 1 is 2, 2 times 1 is 2. It would just be a series of the same number. So if I take this example up here, I want to turn it into a series. I just put plus signs, and now it's a series. And so I would want to add up all those terms together to get the sum. And so everything in the formula means the same as it did when we were talking about sequences. I want the sum of, in this case, 5 terms. So this would be S sub 5. The first term is 3. R is 2, because I'm multiplying by 2 each time. N is the number of terms. So I just said I wanted to find the sum of the first 5 terms. So N is 5. And we use R twice in this formula. Remember, again, I mentioned it when we were talking about sequences. For geometric, it's very important that R is what you multiply by each time. So in this case, you can think about it that we're dividing by 2 each time, but R is 1/2. Okay, so it is true that we are dividing by 2, but R has to be what you multiply by, and dividing by 2 and multiplying by 1/2 are the same thing. Lastly, we're going to be talking about the infinite geometric series, and that is a special case and has a special formula. So usually you'll either just see the capital S or S to infinity, but if you don't see an n as a subscript or some number there, then you can assume that it is an infinite geometric series. The formula is much simpler, but we have a special set of rules. if the absolute value of the common ratio is less than 1, then there will be a sum to our infinite geometric series. But if the absolute value of r is greater than or equal to 1, then there is no sum. We're also going to talk about sigma notation. Okay, so first we're going to go through the arithmetic series. So again, we have this formula. Notice that this formula given here and the formula given here are slightly different. They're the same formula though. It doesn't matter if I multiply the quantity by n and then divide it all by 2, or if I have n divided by 2 and then multiply by the quantity. Okay, it's just a choice of the order in which you do that. So usually I'll pick and choose. If my n is even, then I'll divide it by 2 and then multiply by the sum. Whereas if n is odd, then I multiply by the sum and then divide by 2. So they're interchangeable. They are the same formula. They're just written in a different way. So the thing is about series is once you learn about series, now we know 2 arithmetic formulas. When we learned about arithmetic sequences, we only knew the one arithmetic sequence formula. So if we had a problem that was an arithmetic sequence, we knew exactly which formula to use. But now that we're learning about arithmetic series, we know a sequence formula and a series formula. So sometimes you will have to use the sequence formula to get information you need to find the series. So you want to keep that in mind. It can be bump up the difficulty just a little bit sometimes. Okay, so for example, we want to find the sum of the first 20 terms. That would mean that n equals 20 of an arithmetic series where we have the first term is 10 and the common difference is 3. Well, if I want to find the sum, I'm going to use this formula, and they told me n, great. They told me a sub 1, great. But then they told me d. Well, this formula doesn't need d. So why would they be telling me d if I need the sum and that's not part of this formula? That's to let you know that you will then have to use the sequence formula and the information they gave you so that you can find the 20th term so that you can use the formula to put in there. So if you are working a series problem, but you find they've given you some information that's not necessary for the series formula, chances are that means that you have to go back and use the sequence formula to find the missing information that you need for the series formula. All right, we're also going to talk about sigma notation. So sigma is just a letter of the Greek alphabet. So sometimes it's called sigma notation, but it's also called summation notation. And so when you see that sigma, it automatically means you're talking about a series because the sigma implies summation and series is adding all the terms of your pattern. So the way that this sigma reads is the bottom number tells you where you start with your pattern, and the top number tells you where you stop with the pattern. So 2k minus 3 is the expression that I'm going to substitute into. Notice it's linear. That makes it arithmetic. So in order to generate this series, the first thing I would do is substitute 1 in for k. Then I would substitute in 2, then 3, and I can stop when I get to 4 because that is the number at the top. And then I can calculate. So if you plug 1 in, you get -1. If you plug 2 in, you get 1. If you plug 3 in, you get 3. If you plug 4 in, you get 5. And because it is series, which is what that symbol means, you would then add up those 4 numbers and you would get that the sum is 8. There is also in your graphing calculator, there is a sigma that you can use that is alpha window, and it's number 2. It says summation, and then it's got the sigma notation. And then when you choose that, it gives you places to type in everything. If you have an older calculator, you probably don't have that on there, but it's not something that they've always had. But if you've got a newer calculator, it's alpha window 2 is where you can find the sigma notation. But you should be able to look at a sigma notation problem and figure out how to generate an answer just by understanding the problem. Okay, so let's work through a few examples. So for number 1, they gave us a sub 1, they gave us a sub n, they gave us n. Okay, it says find s sub n. So that's what we need for this formula. We need n, a sub 1, and a sub n, and they gave us all of that. So for number 1, it should be cut and dry. If n is 12, then I'm finding the sum of the first 12 terms. Okay, n is 12 divided by 2 times the first term plus a sub n, in this case, is the 12th term, right? So a sub n is 100, but n is 12. That means that the 12th term is 100. Okay, so you just put the numbers in there and then crank out your answer. So 672 is the answer to the first one. All right, then we get to number 2. So as I mentioned from the example, I'm trying to find the sum of the first 8 terms. I know the first term is 42. I know the common difference is 6, but I don't need the common difference for the series formula. What I do need is a sub n. So I really need to know what the 8th term is. So the fact that they gave me a piece of information that's not needed for the series formula, but left off a piece of information that is needed for the series formula, means I'm going to have to start with the sequence formula. So the first thing I'm going to do is start with a sub n equals a sub 1 plus n minus 1 times d. And I'm finding the 8th term if the first term is 42, n is 8, and the common difference is 6, and the 8th term is 84. Now I have all the pieces of information that I need for the series formula. Now I can find the sum of the first 8 terms. They told me that n was 8, a sub 1 is 42, and now I know that the 8th term is 84. And that allows me to find the sum of the first 8 terms, which is 504. And the third one, they gave me most of the information, but they didn't spell it out like they did in 1 and 2. So for number 3, let's see what I have. I know that the first term is 8. I know the last term is negative 10. So I have a sub 1 and I have a sub n. What I don't know is how many terms there are. That ... is leaving a gap in my information. So that means if I'm missing a piece of information that I need, which in this case is n, for the series formula, I need to start with the sequence formula, and I'm trying to figure out what n is. So the sequence formula is the last term equals the first term plus the number of terms. And I can look at this pattern and see that it's going down by 2 each time. So d must be negative 2. So when I get all the information that I do know into the sequence formula, I can find out that n equals 10. Then I can find the sum of the series, s sub 10, because now I know that n is 10, 10 over 2, and I already knew the first term and the last term. And so the sum of the first 10 terms of the sequence are just negative 10. Because the common difference is negative 2, and we started with a positive number and ended with a negative number, when you add up all the numbers, the sum isn't going to be very big. In this case, it's negative because I have both positive and negative numbers in my pattern. All right, number 4, sigma notation. Okay, so let's see how we can use this notation with the series formula. So when you substitute in the number down here, that gives you your first term. Okay, if I wanted to write out this series, I would start by substituting in the number below the sigma, and that would give me the first term. If I plug in the number on top, that gives me the last term, which is a sub n. And n is always going to be the top number minus the bottom number plus 1. Why the plus 1 is because when you count, then you sometimes, like if you think about, like if you count from 3 to 10, that seems like it's just 7, but you're actually not counting that first number. So you have to add the 1 back. As long as the bottom number is 1, though, then it's just going to be the top number. So 20 minus 1 is 19, plus 1 is back to 20. So it might seem like this plus 1 is not necessary, but it will be if the bottom number isn't 1, and it won't always be. Okay, so to keep going with that, I need top number minus bottom number plus 1 gives me that n is 20. So I'm going to find the sum of the first 20 terms. A sub 1 is what I get when I plug the bottom number into the expression over here. So 2 times 1 is 2 plus 1 is 3. And the top number, 2 times 20 plus 1 is 41. And I can find my answer, which in this case is 440. All right, number 5, the sum of the first 50 positive odd integers. Well, the first positive odd integer is 1. The second positive odd integer is 3. Then 5, then 7, ... Okay, so that is what the pattern looks like. So I know the first term. I know that the common difference is 2. I know that n is going to be 50, but I'm not sure exactly what the 50th positive odd integer is. So I'm going to start with the sequence formula. Okay, so I know that n is 50. So I'm trying to find what is the 50th positive odd integer if the first one is 1, n is 50, and the common difference is 2. And if you do that, then you end up finding out that the 50th positive odd integer is 99. Now, you might have guessed that anyway, but formula will tell you for sure. Now I can find the sum of the first 50 positive odd integers. Again, we know that the first positive odd integer is 1, and we have determined that the 50th positive odd integer is 99. And so the sum is 2,500. One more example for arithmetic. So here I know the sum. The sum is 900. I know the first term and the last term. N is what I don't know. So if I want to use the series formula, I plug in what they give me, and I'll be solving for n. What I really need to know is d, though, right? If I know the first term and they want me to tell you the first 3 terms, I just need what d is. But I have to use what they gave me. So since they gave me the series answer, I'm going to use the series formula, and that will tell you that n equals 20. Well, that's great, but I still need to know what d is. So now that I've used the series formula, let's try the only other formula I know. So a sub 20 is a sub 1 plus n minus 1 times d. I need to know what d is. Well, n is 20, and so 83 must be the 20th term. First term is 7, n is 20, and I can find d. And that way I can figure out that d is equal to 4. And now I can answer the question, what are the first 3 terms? Well, the first one is 7, plus 4 is 11, plus 4 is 15. Those are the first 3 terms of the arithmetic series. Moving on to geometric series. We have a different formula. Remember now this pattern, you multiply by the same thing each time. We still have a sigma notation. Everything is generated the same way, but the expression next to the sigma notation will be exponential. That's what makes it geometric. So let's use our new geometric series formula to do some examples. So for number 1, it says to 6 terms. So s sub 6 equals a sub 1 times 1 minus, looks like we are multiplying by 3 each time. We just said that n was 6. It's a sub 1 and n. And r is 3. And then once you get everything in your formula, you can just go to your calculator. Remember that the sum and the sequencing answers for geometric, don't be surprised if your numbers are really big or really small because it's exponential. For number 2, let's see what we have here. So n is 4. Find the sum of the first 4 terms. A sub 1 is 3. R is 1/3. N is 4, and R is 1/3. Be careful when you're putting that in the calculator. Make sure you try and use like the proper notation with fractions, especially negatives. Just be real careful when your calculator. Once you get all that in there, you're going to get a decimal, but then if you hit math enter, it'll give you 40/9. Okay, next example. So here they didn't give us what n was. They didn't say to 6 terms, or they didn't say n, but they gave us the 5th term. So we can apply that is the sum of the first 5 terms. We know the first term is 2. R is -3. Be careful with your parentheses. We're using 5 for n, and R is -3. So then once we get all of that plugged in, it's 122. All right, so last we got the sigma notation. So it works the same way. This actually example is arithmetic because this is linear, not exponential. It would have to be 3 to the j power to be geometric, but it works the same way no matter what, because they want this to be written in an expanded form, which means you have to write out the whole thing anyway. And if you have to write it all out, you might as well just add the numbers up individually. So it would be 3 times 1, because it says a 1 down here, plus 3 times 2, plus 3 times 3, plus 3 times 4. So our expression in an expanded form is 3 plus 6 plus 9 plus 12. That's the expanded form. And then S sub 4, what you get when you add them all up is 30. All right, for the last one, now we're going to go backwards and write this in sigma notation. If you're writing a sigma notation, always a good idea to just start with n equals 1. Because if you do n equals 1 down here, how many ever terms there are can be the number at the top. And there are 1, 2, 3, 4, 5. So I'm going to write a 5 at the top. And we're actually going to use the sequence formula to help us there. So remember, the sequence formula is a sub 1 times r to the n minus 1. We just need to use that template right here. So a sub 1 times r, and then we're going to leave the n minus 1 because the numbers above and below the sigma tell us what to substitute in. So if you, again, start with n equals 1, then how many ever terms there are can be the number up here. And since this is multiplying by 3 each time, it's geometric. So I'm using the geometric sequence formula as a template and just filling in a sub 1 and r. And you can even try that. If you plug 1 in, you should get 1. If you plug 2 in, you should get 3. If you plug 3 in, you should get 9, etc. All right, lastly is the infinite geometric series. So that implies infinite, that it goes on forever. So if you want to try this example, if you take a piece of paper and you fold it in half and tear it, and then take one of those halves, fold it and tear it, and keep doing that. So you keep taking half of your result and tearing that in half again. Well, you get to a piece that is so small that physically you can't even really tear it anymore. But that doesn't mean that it disappears completely, right? There's still matter there. You guys know that from science. So there's still something there. It's just really, really small. That's an example of an infinite geometric series. So if we were to graph, this is an infinite geometric series, but we want to graph, this is n, and then this is going to be, we're going to do a sub 1. So the first term would be 1 comma 1/2. because that's a sub 1. But then the next thing is going to be 1/2 plus 1/4. So each time our next point is going to be the sum. So it would be the sum of the first two terms. We'd go for n equals 2, and that would be 3/4. And then each time you keep adding. So the third term would be 1/2 plus 1/4 plus 1/8, which is 7/8. And then the fourth term would be 1/2 plus 1/4 plus 1/8 plus 1/16, which is 15/16. Each time you add, it's going to be the numerator 1 less than the denominator. So next would be 31/32. And as you keep going, that's going to continue to be the pattern. So we're just going to get closer and closer and closer to 1 each time. And that's how an infinite geometric series works. So we have a different formula if it's infinite. It's S sub n equals a sub 1 over 1 minus r, the simplest of all the formulas. The catch is that if the absolute value of the common ratio is greater than or equal to 1, then the series has no sum because it just keeps getting bigger and bigger and bigger. That would mean like if you multiply times, if absolute value of r, let's say you're multiplying by 3 each time, the series is just going to keep getting bigger and bigger and bigger and bigger. So it would approach infinity. So it has no sum. You'll learn more about that in pre-calculus. So right here, we have a sigma notation. Notice that it's going to infinity. So that's how we know that we use the infinite geometric series formula. Based on the last problem we did for geometric series, we know that this is kind of fitting the model of a sub 1 times r to the n minus 1. So we can imply that a sub 1 equals 1 and r equals 1/2. So the absolute value of r is 1/2, and that is not greater than or equal to 1, so there is a sum. Okay, so the r value should be the base of the exponent, and as long as the absolute value of that base of the exponent is less than 1, you can use the formula. So s, usually don't even put a subscript if it's infinite, just imply that it's infinity, and the formula is the first term. If you put 0 in, that generates the first term, and anything to the 0 power is 1. And then r is 1/2, and our answer is 2. So here, a sub 1 would be 2, and r equals 6/5. Well, the absolute value of r here is greater than or equal to 1, so there's no sum. It's important that you pay attention to that, because if you do use the formula, you'll get an answer. It just won't be right. So you want to make sure you catch it at that point. Let's do a few more examples with infinite geometric series. So find the sum of each infinite geometric series if it exists. So first thing you do is check the value of r to see if its absolute value is less than 1. So the absolute value of r is less than 1, so we keep going. S equals a sub 1 over 1 minus r. And the answer is, if you put it in your calculator, again, you're going to get a decimal, but if you hit math enter, it will give you your fraction, which is your exact answer. Here, the absolute value of r, again, is less than 1, so we keep going. S equals a sub 1 over 1 minus r, and our answer is 8. In number 3, we have to figure out what r is. So if you don't know what r is, and you can't tell just by looking, you can always take any term and divide by the previous term. Okay? With arithmetic, take any term and subtract the previous term. That will give you the common difference. With geometric, any term divided by the previous term, and that will give you the common ratio. So here we can figure out that r is 5/6. The absolute value is less than 1. So s equals a sub 1 over 1 minus r, and our answer is 4/3. Again, you're going to get a decimal on your calculator. Just hit math enter. Last set of examples. Find the first 4 terms of each infinite geometric series. So we have the sum already. We need to know the first term. but we know the sum and r. So we can use the formula to go back to find out what a sub 1 is. So this is 3/4. Multiply both sides by 3/4, and a sub 1 equals 12. Then I can write the first 4 terms, because now I know the first term is 12, and then you would multiply by 1/4. So then your next term would be -3. Multiply by 1/4 again, you get -3/4. Multiply by 1/4 again, and you get -3/16. Try one more time. 48 equals a sub 1 over 1 minus -2/3. That will give us that a sub 1 equals 80. So now I know my first term is 80. I'm multiplying by -2/3 each time. So 80 times -2/3 is -160/3. Multiply that times -2/3, you get 320 over 9. Multiply that times -2/3, you get -640 over 27. Avoid rounding wherever possible. Last one. 33/4 equals a sub 1 over 1 minus 1/3. So this denominator equals 2/3. You multiply both sides by 2/3. You get a sub 1 equals 5.5. So then you can write your terms 5.5. Multiply that times 1/3. You get 11/6. Multiply times 1/3, you get 11/18. Multiply by 1/3, you get 11/54. Okay, so there's some practice problems that are loaded in there. The key is provided. If you have any questions on anything to do with arithmetic or geometric series for the notes or the practice problems or the assignment that's due at the end of the week, then please attend office hours or send me your question through email or Schoology message.